I want to start. I'm going to give you two stories. The first one, I am originally from Mexico. My wife is from Canada, from Montreal, where he started, where you grew up there, right? Yeah. When we moved to Texas, because we've been moving all over the place, when we moved to Texas, we bought our first house, and we were very excited. We got to the back, beautiful yard. We paid the bank and everything. We went back to the house, went out to the backyard, looked at the grass, and it looked funny. We're used to this nice, lush grass where you can just walk and enjoy that, beautiful softness. Well, this actually wasn't really like grass. It was runners and very thick blades. And we were like, what is that? So we decided, well, we should probably replace it with something that is better. So we went in the next day after we bought the house, starting pulling those runners out, pulling them. We got about 2 bags. It was only a little patch that we were able to get out. And we were just thinking about it, like, why is this here? I mean, it looks like it's been there for a long time. And then we called a friend. It's like, could you come and help us figuring out what's this all about? And then the friend comes. She was living in Texas for a long time. And she said, well, this is called St. Augustine grass. It's the most expensive grass that you can grow in the Texas hot weather. So we were like, okay, we'll leave it there. And that story is a little bit on how the microbe and human relationship has been. We're going to get into that. But my goal in this talk, you know this verse, I will praise you because I'm fearfully and wonderfully made. Your works are wonderful, I know that full well. Well, after this talk, I hope that you will gain a completely new dimension on how profound this verse is with the design of the human body. All right? So here we go. We know the human body is fascinating. That's what I've been doing for all my professional life, and it is every time I see how the body works, it just blows my mind. This was known to, the painters. Leonardo da Vinci was the first one to really make very good sketches, not only of the outside of the body, but also the inside of the body, figuring out how things worked in the body. Leonardo and Andreas Vesalius did some drawings that helped us really look at all the elements. And it just increased our awareness of how intricate that design was. Later on, this is actually a picture from William Harvey. William Harvey was probably the man who made the best observations on how does the cardiovascular system work, okay? Later, when we were able to develop other little instruments like microscopes, we were able to peek a little bit into what was really the smallest components of the human body. So Leeuwenhoek actually used this microscope, and he actually took some samples from his mouth to see, well, what is in the mouth? And what he found was actually multiple things. He called them the animalcules. And he described them as very little living animalcules, very prettily a-moving. So he found the first observations of plaque. He did some sperm, some other elements that he found also in nature. And then Robert Koch gave a little bit of a better boost for what we call the germ theory of disease. That is how germs cause specific problems. Now, later on, I put Lister here. Lister was the first person to find that there were antiseptics. This means there were substances that were able to decrease the risk of infection, decrease the risk of all these puerperal fever things, etc. And Lister is going to play a little bit of an important role in the rest of my talk. When people found that germs caused disease, there was a little bit of a panic going on. And I'm sure you've seen this. This is actually, oops, sorry. Let me go back. The caption on this says, "Microcosm dedicated to the London water companies, full of hydras, gorgons, and chimeras alike." So there was a thought that germs were bad. Now, my personal story on that one, when I grew up in Mexico, I used to have a lot of sore throats. And actually, during the podcast, you were asking me, how did you decide to become an infectious diseases physician? There were many factors, but I think this was one of them as well. So as I was growing up, I would get a sore throat, and the very next thing that would happen is I would go to the doctor, and the doctor said, aha, sore throat, bacterial infection, you need penicillin. This was penicillin shots twice a day for 5 days. Let me ask you, how many sore throats did you have when you were growing up? So I feared getting close to someone who was sick because I was afraid I was going to get the bug and I would get more shots. That was scary. And I carried on that. But, growing up, realizing that really I was not the only one that had that fear, because I see, for example, antimicrobial soaps killing 99% of the germs. There's this idea that the more germs you kill, the better you're going to be, the healthier you're going to be. Well, the question is then, if you try to kill all of the germs of your body, how many germs or how many bacteria really would you be killing? So, and if you killed all the bacteria, then what would be the consequences? So let's go back and see. The human body consists of about 30 times 10 to the 12 cells. The great bulk of those cells are the erythrocytes, which are the red cells that go through your blood. They compose about 25 times 10 to the 12. If you see, for example, the muscle cells are a very, very small amount. Neurons are a very small amount as well. So if we wanted to represent something like this, we would say, well, there's about 30 times 10 to the 12 human cells. 25 of those, 25 times 10 to the 12 of those are the erythrocytes. 5 of those are the rest. How many bacterial cells are in our body? 38 times 10 to the 12. That means you have more bacterial cells on your body than human cells. Now, this doesn't mean that you can use antimicrobials to lose weight, because really, the weight of those bacteria is only 0.2 kilograms total. So even if you use the antibacterial soap, sorry, you're not going to lose weight. So where are those cells? Where are those bacteria? They are essentially covering all of your body. The gut is the main repository of bacteria. It has about greater than 1,000 bacterial species. The oral cavity and the airways have about 500 or more. The skin also has a significant amount, about 300. The urogenital tract is also lined with some bacteria. So they are all over us. So if we estimate that most of the cells in our body are bacterial, and some of them are human, we call the bacterial cells that are in our body the human microbiota, all right? And the differentiation is this. If we took the genes that those bacteria have, and we count with them all the genes that the human cells have, actually the human genes are only a very small fraction of all the genes in all the cells in our body. So there's about 2 million bacterial genes for 23,000 genes. As you can see, we are in very close relationship with bacterial products. Not just the bacteria, but now we're talking about the bacterial products. In a way that some researchers have said that humans are really superorganisms whose metabolism represents an amalgamation of microbial and human attributes. And another researcher from Cornell University says, the gut microbiome, now referring only to the bacteria in our gut, it's said to encode a second genome, and its functions expand the host's physiological potential. In the gut, microbes extend digestive capabilities, prime the immune system, produce vitamins, degrade xenobiotics, and resist colonization by pathogens, which are the bad bacteria. So how do we get all these bacteria? The very first thing is maternal health is important, because it is thought that a baby inside in utero is sterile. And as soon as it comes out, it is exposed to bacteria. And depends on how that baby is born, the exposure to bacteria is going to be different. Vaginal delivery will expose it to the bacteria on the skin and the genital tract. A cesarean delivery will be more sterile. There will be less exposure to bacteria on the baby. Why is that important? Well, we know that children born by means of cesarean section have an altered microbiota, and they may be more susceptible to obesity, diabetes, allergy, and asthma through childhood and adult life. Thankfully, all my girls were born by cesarean section. Thankfully, that's not the end of the story. The infant feeding method is also important. When breastfeeding actually provides the baby with microorganisms, antibodies, immune cells, and cytokines that actually will protect the baby in the early stages. So bottle feeding doesn't do that. Breastfeeding also starts giving the baby exposure to different bacteria on the skin of the mom that will be going into the gut. And that will start forming the first gut microbiota of the baby. So the differences are important, and I want to show you what happens with the immune system and the bacteria meet. This is a schematic representation of a computer motherboard. And I don't know, I like to, whenever my computers die, I like to take them out and just look at these little elements inside and see how they're intricately, connected one to the other. And to me, it is always amazing to think how much thinking went into the design of all of these little things. Well, let me show you. This is the schematic representation of all of the signaling pathways of only one cell in the immune system. The orange ovals around are essentially signals that will be processed inside the cell through chemicals and will have an output. Those pathways are very complex. Fuss and I we could attest the fact that immunology is like, wow, it's like way out there in all of the biological science. It's extremely complicated. The immune system that we have, though, we are born with the fundamentals of an immune system, but when we come out, that immune system actually is trained by the bacteria on our bodies to become the fully developed immune system that we have as adults. So let's go on how this goes. The adaptation process, then, all that training process starts as soon as we are born. There's bacteria that we'll encounter, and those bacteria will start covering our skin. When a bacteria establishes itself on the skin, we call it's a colonizer. Means it has made a niche somewhere on our body. This is a very important concept, colonization. So bacteria that come on the skin, they don't cause disease. We call them colonizers. One of the most famous ones, one of the most important ones, is something we call Staphylococcus Epidermidis, which I am going to refer to as Staph Epi. That's what we call it for short. All right? When Staph Epi comes on our skin, it starts producing some antigens. And those antigens are going to be picked up by dendritic cells, which are cells of the immune system. And that is where the training starts. The dendritic cells will present some of those proteins, some antigens, to the regulatory T cells, and it'll create a status of tolerance. So the body will learn to tolerate those cells on the body. And how does it prevent it from just the bacteria taking over from our body? Well, bacteria produce waste products. In this case, they're called small-chain fatty acids. When the small-chain fatty acids start to pile up, when the trash from the bugs are starting to pile up, the immune system will trigger some inflammatory pathways that will actually start killing the excess bacteria. And then there will be an established population, an equilibrium between the body and the bacteria in our system. Now, there is also a very interesting relationship between the Staph Epi and the skin cells. Staph Epi stimulates the production of antimicrobial proteins from the skin cells. That is, Staphylococcus epidermidis will signal to the skin, hey, you need to produce these chemicals to prevent the bad bacteria from coming over. Also, Staph epi produces itself other antimicrobials that prevent the colonization and infection from more pathogenic bacteria like Staphylococcus aureus, or Staph aureus for short. We don't like Staph aureus. That's a very nasty, nasty bug. This is also fascinating. It just came out very recently, that Staph epi actually produces other peptides, other chemicals. In this case, this is called 6N-hydroxyaminopurin. And this has an anti-tumor effect. So in mice, this chemical actually prevents the resurgence of tumor cells that are induced by ultraviolet radiation, meaning that right now, the bacteria on your skin may be protecting you against tumors induced by ultraviolet light. And finally, Staph epi also plays a role in wound repair. When you get a wound, there has to be a balance between, okay, we need to attack what is not supposed to be there, but then a repair mechanism, the backing up and say, now let the normal body take its course and finally lead to healing. So it encourages the cytotoxic T cells to produce antimicrobials, and it also produces some other proteins that will help in the healing of those wounds. Okay. This training happens in a very short period of opportunity. These are experiments that were done in mice, and I want to show you how interesting this thing is. That window of opportunity in mice is only in the first 2 weeks of life. In humans, that would translate to about 1 to 3 years. So there is this window of opportunity in which the immune system needs to be trained adequately. If we start with a germ-free colon, we're going to be looking at the iNKT cells, or cells from the immune system. If they are not exposed to bacteria during the critical period of the window of opportunity, there will be a susceptibility to colitis in the mice when they grow up. If we introduce the right diversity of bacteria before the window of opportunity, then the mouse will develop a healthy colon. If that diversity of bacteria is introduced after the window of opportunity, there will be a susceptibility to colitis. Now, if we introduce bacteria, just one kind or two kinds, not a diverse population, that will also lead to a susceptibility to colitis. This is the colon. The lung is exactly the same, but it will translate itself as asthma instead of colitis. We need the right exposure, be at the window of opportunity with a diverse amount of bacteria so we can develop a healthy immune system in the lung. There is also, on the other branch of the immune system, the antibodies, very similar effect. And this one translates to anaphylaxis. I don't know if anybody knows what anaphylaxis is. For example, if you heard this term about peanut allergy. Some people eat peanuts and they develop this allergic reaction that can kill them. Well, that could be mediated by the microbiota. If you are not exposed to the right antigens in the window of opportunity, your immune system may not be trained adequately and may end up with the susceptibility to anaphylaxis. So, it is now increasingly clear that early life colonization also coincides with a potentially time-limited period during which the immune system is permissive to microbial instruction. And the development of defined arms of the immune system has coincided with the acquisition of a complex microbiota, supporting the concept, and this is from an evolutionary standpoint, that a large fraction of this machinery says it's evolved as a means to maintain a symbiotic relationship with these highly diverse microbial communities. You know, I stopped and thought about this, and I was like, you know, if you're talking about evolution, which is a very, very complex system, now you're bringing so many other organisms into the mix. To me, it's just mind-boggling to think that evolution itself can just account for all that. I'm having trouble seeing what the mechanism for this is. Okay, but the story's not over. Baby has been breastfed and now it's growing up. Where you grow up, it also will tell you, or will tell us what kind of immune system you're going to be developing. Growing up in a rural area you will be exposed to animals, you'll be exposed to other worms, you'll be exposed to other things. If you grow in an urban area, your exposure to all these different things is going to be different. So in studies that were done in the microbiota of children in a rural area, which was Burkina Faso in this case, and an urban area, which is Florence, Italy, there was a higher number of bacteroidetes. These are the diverse bacteria that we need. Whereas children growing in an urban area have a smaller amount of those. That means the microbes that they're exposed to is a much more limited kind, a much more limited species. And this is what happens then. We've seen that with modernization. If you look at the yellow line would be a country with minimal modernization. The blue line would be the United States. As time goes by, the diversity has been coming down. Right now, we are in a very low diversity area. We still have the possibility, as the dotted lines say, to increase that diversity. But as countries modernize, which is the red line there, they start to follow the same path that the United States has been following. And how does modernization impact all this? Well, water sanitation was important. Water sanitation prevents us from having all those diarrheal diseases, but it also limits our exposure to other kinds of bacteria. We have less exposure to animals in an urban setting, less exposure to parasites. We have smaller families and fewer children. And this is important because the more children that there are in a family, there's more exposure. And there seems to be kind of a quorum on what are the right bacteria that every member of that family is going to be able to tolerate. So one child doesn't expose to as many pathogens as a family of many children. And of course, the one that has been present for the last 50 years or so has been antibiotics. Antibiotics have transformed our life in many ways. Thanks to the antibiotics, we've been able to actually cure many diseases that were once fatal to humans. The problem is antibiotics have to be used lightly. They cannot be used all over the place. Otherwise, we are modifying the microbiota, especially in the early years of our life. Antibiotic use within the first 6 months of life is associated with an increased susceptibility to allergy and asthma at 6 years of age. Exposure during the first year of life is associated with the development of wheezing and eczema at 8 years of age, even after taking into account early life respiratory infections. Exposure to antibiotics, especially during the first year of life, associated with an increased risk for development of inflammatory bowel disease. This is called Crohn's disease or ulcerative colitis. And during the first year of life, also associated with increased susceptibility to being overweight and developing central adiposity, may lead to increased development of type 2 diabetes mellitus later in life. So overall, medically important antibiotics accounted for 62% of all antibiotics sold for use in food-producing animals only in 2015. So most of the use of antibiotics is actually in animals, not even in humans. And 70% of all medical important antibiotics in the US are sold for use then in those animals. Okay, we're going to talk now what happens when you're an adult. So you've grown up, you're born, you breastfed or end up in California. How does this apply now to someone like us? There are many factors that are influenced by the human microbiota. I'm going to be touching only on a few of these. When we can start with obesity. Also in rats. This was a fascinating story on how the finding that antibiotics actually made animals bigger. It was actually in chicken. There was a company that was trying to look for production of B12 vitamin, and inadvertently they gave some chicken the B12 that was actually laced with a little bit of antibiotic, and they found that the chicken would gain weight 50% faster than the animals that did not get any antibiotic. So we know now that antibiotics actually, a low dose of antibiotics increase the weight of animals. And that was actually a very welcome thing for people in the animal husbandry industry. So in these experiments, there were mice that were given antibiotics would become obese. Now, if some of these mice were given a high-fat diet alone, they would stay lean. But if they expose these mice to a low diversity bacteria, they would develop obesity. If they would expose them to a high diversity bacteria, they would stay lean. So it seems that there are pathways that are mediated by the bacteria that will end up deciding whether you're going to be gaining weight in the future or not. One example is, for example, this, and this is one of the ways that we've seen how what we eat really affects our bodies. The chain on the top would be a complex carbohydrate. If we eat complex carbohydrate like fiber, those actually will feed the good bacteria. Some of those complex carbohydrates can be taken up through the cells, and they'll end up on a certain kind of metabolism in the liver. If we eat, let's say, the simple sugars, they will actually not feed the good bacteria, and therefore the bad bacteria will take over. Those simple sugars then will come through and cause other problems with the metabolism in the liver. It will cause some fat accumulation. It'll cause also the adipocytes to take more fat, etc. So yeah, that can promote obesity. The bacteria, the low diversity bacteria, can also produce some products, in this case also something like small chain fatty acids, that will be picked up by the liver, also causing some problems in brain signaling and liver metabolism, and also can alter the immune system by causing a state of inflammation in the lining of the intestinal, of the gut. And that inflammation seems to be a positive feedback effect to promote for the bad bacteria to continue thriving, which seems to be one of the mechanisms in inflammatory bowel disease. The low diversity bacteria will produce certain products that will activate inflammation, and that inflammation will then result in diseases like Crohn's disease. Diabetes also has a very similar pathway here. Some bacterial products seem to cause alterations in the metabolism of some chemicals in the liver, and also activation of inflammatory cells. Atherosclerosis, very similar story as well. There's some products that will leading to inflammation, leading to alteration in liver metabolism, and also in plaque formation directly. That was also very interesting, how bacterial product will make your body produce chemicals that will cause accumulation of plaque in your arteries. The last one we're going to be touching on is going to be the emerging infectious diseases. I'm not sure if you are aware of this bacteria. This is called Clostridium difficile. Clostridium difficile, if you're exposed to it, it'll give you the most horrendous diarrhea you've ever had. And sometimes this diarrhea is fatal. We've seen, this was usually a bacteria that we used to find in hospitals when people were on antibiotics and then they would be exposed with C. diff. We're starting to see a lot of these infections in the community. So they may have taken only one antibiotic, just one dose. And then weeks later, they come to the hospital with this raging C. diff infection. So the combination is if you're exposed to antibiotics and you are exposed to this bacteria, you could end up in the hospital very sick. How do we treat C. diff? Well, we treat it with other antibiotics. We treat it with something called monoclonal antibodies. But we also treat them with something called fecal microbiota transplant. What is that? Well, we get healthy donors who give their poop. It is processed, and through a colonoscopy, it is put back in the colon of the person that has the disease. How good does it work? 85% of the time, it works. Way better than any of the other treatments that we have. Just to go back and figure out how amazing that if we use just the same things that our body had from the very beginning, we're going to go back to a healthy state. There are a couple of unanswered questions. What is the role of viruses? We're starting to learn a little bit more about what are the viruses now doing in our body. And I guess AJ must know much more about that than me at this point. But also there's other elements, other microorganisms in our bodies, which are, for example, protozoa. We still don't know what those are doing. So in conclusion, the bacteria that constitute the normal human microbiota are especially designed to maintain human health. The bacteria in our microbiome are established early in life, and they play an important role in the training of our immune system. The microbiota influence many aspects of human metabolism, and their disruption can lead to chronic diseases. Our antibiotics are very powerful tools to combat disease, but they have to be used carefully because they disrupt the balance between our body and our microbiota. Our microbiome is an extension of the design of the human body. So it's not just our human cells that is wonderfully made. Now we have to account for all of these other cells that actually make us healthy. The microbiome gives us an insight on the complex design that includes an element of plasticity in the immune system. The immune system comes out, when you come out, there's still some training that can be done. Whereas some scientists would explain the relationship between humans and bacteria by symbiotic coevolution, this seems to be adding another layer of complexity to the evolutionary paradigm. And the microbiota is another example on how the natural world has been created for the benefit of human beings.